Okay, thank you for the introduction. And I would like to begin with to say thanks to the organizer for inviting me here. So, okay, I'm from IIT BHU, and okay. So before I begin, this work is actually done with Professor Wolfgang Welzig in Germany, Kunsthal University, and also with other two experimentalists, Professor Deflev and Roman. In KIT Germany, okay? And the topic of that talk, as you see, the multi-terminal Josephson junctions with tunable topological properties. So this is actually the system we are going to actually discuss. We have one which is the green region, where we have the normal region, and there are 4 superconductors attached to it, okay? And as you see here, these curves is actually the 4 of them. It is actually gate is actually applied to control the electron inside the system. Okay, so let's begin with. So here are the contents. So first, actually, I will introduce for the students. It will be, I think, better to actually give the introduction, and then I will actually model the system, and I use square and graphene lattices. And then the method actually we use mostly, I am going to discuss this scattering matrix theory, and then of course this Broglie-Bode designs in particle and whole space, which is actually just to complement the scattering matrix theory, and then the results, and later I will summarize it. So let's begin with. So to understand the Andreev reflection first, so for example you can assume, so suppose in this x direction, suppose there is a normal metal. And in this, of course, in other half of the x, suppose you can have insulator. So as insulator has gap, if you excite electron with certain energy, it cannot go to the insulator, right? Because there is a gap inside and there is no states present there. So it will reflect back, and it reflects in the specular manner. But if you replace this insulator to the superconductor, as we know from previous talks, we have enough discussion. The superconductor have a gap, right? But inside the gap, there are special particles, or you can say the 2 particles, or as a super Cooper pair. So even you have the gap, but their Cooper pairs are present. So suppose you excite from the normal regions of electron, and if it hits the barrier, the chance is actually, of course, it can actually reflect as an electron, but of course it can take one more electron from here and goes as there as a Cooper pair. Okay, and then the vacancy actually creates in the normal region is kind of reflected. So like whatever the path actually electrons goes, it seems that there is a hole reflected from the back, and this kind of actually reflection is known as retroreflection, because actually it's retracing the path of the electron, and this phenomena is known as actually Andreev reflection. And due to this process, even this electron has the less energy than the delta, you can actually find some conductance. Here is a differential conductance is shown. Okay, so within the gap, even you have some finite conductance. Okay, and okay, so this is actually the case for if you have something like very normal metal. But if you replace the metal with the graphene, so here it's not shown, but actually pictorially I want to show. If you have the graphene has 2 bands. Okay, so one is actually the conduction band, one is the valence band. You can say if the electron is actually excited from the conduction band, depending on the actually doping of the system, we can actually have the hole from the actually valence band. Then actually whatever the process you are seeing here, actually it goes in a specular manner. Okay, so this one is actually this is actually predicted, but so far actually there are various experiments, and still it's not fully resolved that there exists specular Andreev reflection, but theoretically yes, it should actually exist. Okay, and you see here also this transconductance actually or like differential conductance is plotted, and we have within this gap 0 to 1, we have some finite conductance there. Okay, but what happens if you replace one more superconductor? So for example, you have the normal region and there is a superconducting region, and you replace one more superconductor. Okay, When you replace one more superconductor, of course, the superconductor has phase, and they might have the phase difference. Okay, so suppose we have the phase difference. So to understand, actually, then there is a formation of earlier it was Andre reflection, and now it is the formation of Andre bound states. And what happens here in the superconductor, you see this is actually density of state plotted in the this direction, and this is the energy scale. And you see in the gap there are Cooper pairs. So what happens from the normal region, the electron goes and it actually hits this barrier. So basically this barrier, and it is reflected as a hole. And when the hole actually goes to hit actually this superconductor, it is reflected as an electron. So it forms a bound state. And this bound state is actually known as Andre bound state. And it happens only when this electron has energy less than the delta, delta of the like the Cooper, the energy gap of the superconductor, basically one of the superconductor. So this, in the simplified picture, one can also understand if you attach, for example, normal as a quantum dot, and you have just one label, and then this superconductor has the phases also. So whatever the label we have in the particle host basis, we have the two energy modes. So you can say at the 0 phase, we have the two energy. One of the curve you can look, let's say this one. And if the dot has 0 energy, with the phase, if you change the phase difference between these two superconductors, it can go down and touch at the 0 energy, and then later actually it can go away. Okay, but the interesting thing is actually if you have the finite energy on the dot, then no matter what's the phase difference between the two superconductors, it never closes. Okay, so we have always the gap. But this idea actually extended, and then suppose let's add more superconductor. Okay, and then what happens to the gap? So this idea is in this paper, in this Nature paper. So suppose we have this again the normal region, which is the scattering region we call it, and you attach many superconductors. Okay, and one of the superconductor is suppose biased, then these are actually act as actually phase differences. So what happens depending on actually these phi 2 and phi 3, maybe there will be gap, but if you change these values, the gap actually closes. Okay, okay, and if you further change, maybe it again it will open. Okay, and what happens? This is not a normal actually gap closing. It actually acts as actually topological property, and there is a gap opening and the gap closing, and again gap opening. And this is actually the transconductance actually they actually calculated, and they find this transconductance is actually we can actually assume this as Chern number there. So we will describe what is the Chern number, how to calculate it. But you see here the transconductance actually if you change the phase, one of the phase. So suppose you have only 4 superconductor, one is grounded, 2 are actually variables which can be actually added in the Berry curvature, and then the Chern number or the transconductance actually first gives the 0, which is the normal phase topologically, and then you have the non-trivial actually phase, which actually quantized in a manner which gives exactly integer value either +1 or -1. Okay, but this was actually the prediction, and then the group in Constance, they actually model this with just single dot, and then and the minimum you have at least the 4 superconductor to have this topological property. So they found that minimum we should have actually at least 4 superconductors, and it's not enough to actually just directly link the superconductor with the dots. We have to actually also link the superconductor itself. So between the superconductor we should have actually some kind of hopping, and then you see here. So this is the energy, and this energy are calculated in the phi 1 and phi 2 space for various values of the phi 3, and this one is actually one can ground it or gauge invariant. So you see here the gap, and then there is a gap closing, and again there is a gap opening, and later there are 2 points where actually it closes. So in the phi 3, if you scan the phi 3, a certain value of the phi 3, you see this 1 point where actually gap closes here, and there are 2 points, and then again 1 point, and these points are known as actually while points. You can actually relate to these phi 1 and phi 2 and phi 3 as a quasi momenta, like k1, k2 and k3, or kx, ky and kz if you want. And then if you sum over, and you can calculate again the Berry curvature, and then sum over this phi 1 and phi 2, and for the different phi 3 value, you see again the Chern number, which is actually you get some finite Chern number. Okay, so and then okay, so but experimentally it was actually suggested actually this coupling between the two superconductors actually messes many things. So it's very hard to do it. And then there was another proposal. So let's have not only one dot, we have the two dots, and the dot actually somehow have hopping between them. It is the R here. Then actually this superconductor can be actually free, and they are not directly linked. Okay, and then they found that because we have the two dots and we have the 4 bands, 2 positive and 2 negative, and you see here actually the phase diagram between, again this phi 0 is again biased to 0, and then with respect to the phi 3, and of course this hopping between the two dots, you see the topological phase transition, which is the black one is -1 and white region is actually 1, and this gray one are actually 0. And again here they observed that there are two wild points. One is actually single and there is another which is double. And these points actually, when you actually transition from this trivial to non-trivial in this axis, you see actually only single wild points. And here if you scan from this topological again non-trivial to 1 like -1 to +1, it directly goes -1 to +1, you have actually two wild points. Okay. But again, the question was actually how to actually deal with this hopping in the experiment. So what actually we again suggested, let's look into any 2D two-dimensional material and try to actually find out if we can actually make a quantum dot kind of system there to observe this topology. Okay, so this is actually the system we consider. And again, as I said, we have the 4 superconductor, and these are actually gated, and the gate potential actually is actually you can actually understand by this formula, which is the Vg is actually the strength of the gating potential, and this is the x direction and this is y direction, and the gates are actually along this diagonal. Okay, which is actually which has actually the value of del along the diagonal, but inside it's kind of 0. So you can see if you probe along both the direction of the diagonal, you have kind of creating a dot there. Okay, and then we actually use two lattices, so square and graphene, to model the system, and we model actually with just simple tight winding Hamiltonian, where actually you see here the first term is actually the hopping term between site R to R plus delta here, and then there is a 4T we put the on-site energy, there is a chemical potential, and this VR, which is only applied only in the normal region, not in the superconductor, and this superconducting Hamiltonian, which is actually S-wave pairing, it is applied only in the superconducting region. And this is actually also for the graphene. Of course, we have the 2 sublattices, and then actually one can write actually tight binding model. It's the same model, but it's in the so red you can assume the A side, and the B you can assume the black side. Okay. So just one second. Yeah. So what's the method actually we use to actually calculate the Andrew bound state? We use this scattering matrix method to understand that actually this will give you only the Andrew bound inside the gap states. So here actually is the equation where is actually scattering matrix for the normal region, and this is a normal scattering matrix, and this is the Andrew scattering matrix. This normal one actually you can assume if the electron goes from the normal and hit this this superconducting barrier, it can actually reflect as an electron, or if a hole goes and it hits this region, it actually reflects as a hole. So this is actually the electron space, and this is the hole space in this scattering matrix. But this one is actually the Andrew reflection, where if you go to the electron and come out as a hole, and vice versa also. That's why it's the off diagonal term. And then in some short junction limit, short junction means the length of this normal region has to be much less than the superconducting coherence length. Okay, in this region, these scattering matrices, which actually depends on the energy, it can be simplified, and it depends independent of the energy. And then one can find this eigenvalue equation. Once you solve this eigenvalue equation, you get some complex energies. So where the complex, the imaginary part actually contains the Andreev energies. Okay, and sorry. And the second method we actually apply that we do not care, and we actually consider only very large superconductors on the both all the four sides, and then but it's finite, and we directly write in the Bogoliubov-Digens form, where this part is actually electron particle part, this is the whole part, and they are coupled by the superconductor. And then we take the finite system, and we fully write, as you saw, we have the bilinear Hamiltonian, and we can always actually diagonalize it, at least numerically, to get the single particle energies. And once we get the single particle energy, okay, these are the parameters actually we use. Once we get the single particle energy, we segregate these energies which are inside the gap. Okay, those energies which are inside the gap, as a function of phi 1, phi 2, and phi 3. And then for different value of the phi 3, of course, we get the energy and also the eigenstates. And with the eigenstates, actually, we calculate the Berry curvature. And once we summed or like integrate out this phi 1 and phi 2, we get the Chern number, which is, of course, the Andreev bands dependent. And once you sum, so at 0 temperature, you can sum all the negative bands, and you can get the ground state total Chern number, which is actually related to the transconductance of the system. Okay, so here is the first result, and first what we want to look, suppose we do not apply any gate potential, then for certain value of the chemical potential and of course the phi 3 value, we see only two bands inside the gap, which are Andreev states or Andreev bands, you can say, and they are gapped. Okay, for certain value of the phi 3, which is here, actually it closes at one point, and again it reopens as a gap, and then again closes at exactly at pi at the 2 points. So we here again see in this system 1 Weyl points and 2 Weyl points, and which is actually we also calculate then the Berry curvature, and you see at the phi is equal to 0 for this curve. So one of the we actually calculate for the negative energy, we see that there is actually positive contribution, and similarly at the negative contribution at the two values of actually phi 1 and phi 2 values, and this cancel out. Okay, so there is a no Chern number here, and here also somehow overall sum is 0. But as you see, once you pass this this transition point, both are pointing in the same direction, you get the some finite Chern number. And of course, once you pass actually this pi, it's actually get the negative Chern number. Okay, so here is actually the phase diagram. Phase diagram of this Chern number, which is actually plotted in the x direction phi 3, and this one is actually whatever this eta we are saying, it's actually related to the actually the chemical potential of the system. So what you see for certain chemical potential energy, it doesn't give any Chern number, but if you have sufficient energy, then you actually, if you scan the phi 3, you go actually trivial phase to actually non-trivial phase, and again the topologically again non-trivial phase, and then the trivial phase. And even if you scan along this direction, you get you get actually the topological transition here. And these are actually some cuts around these values, eta is equal to 0.2 and so on, and you see clearly there is a ground state Chern number is actually non-zero for certain values. And this one actually just to complementary, actually we scan what is the minimum value of the energy, and we find exactly where it becomes 0. It actually complement with the phase boundary condition there. Okay, and sorry, is it not working? Oh, yeah. Yeah. So when we actually turn on this gate potential, we find that if we start with some finite churn and finite topological region, it actually survives for long value of this gate potential, which is around 20 of delta, 20 times delta, and then it becomes, of course, it actually goes away, because what happens, it actually gauge and make it just single dot, and as the superconductors are not coupled, they will actually give you actually trivial phase without any topological condition. And this is also true here, the same result. And oh, sorry. Yeah, and same is true for the graphene. So graphene, we actually first probe without the gate field. We find some non-trivial phase transition from trivial to non-trivial, and of course we get once we actually turn on, again it survives for the longer value of gate potential. And this is actually the comparison between this. So far the result I have shown is only from the scattering region, scattering matrix method, and these actually open circles are actually calculated from the BDG result. It's perfectly matches with the result which actually we got from the scattering matrix. And with that, the summary is that we can actually experimentally relevant. So, for example, gauging, of course, actually putting this gate potential, we can control the topology in two-dimensional system, which is actually it's to begin with the material. There is no topological material, but with the help of these superconductors, we can create the topology, and we study the topological properties. And of course, it can be actually gate tuned, and you can actually tune, you can actually create and destroy the actually topological properties. With that, thank you for your attention.
Yeah, session is now open for question. Hello sir, interesting talk. So initially you mentioned that this phi 1, phi 2 of superconductors is like similar to K1, K2 in general.
Exactly. So it's kind of, you can draw the analogy between actually the K1, K2, and K3 to the phi 1, phi 2, phi 3. It's kind of momentum space. It works as a actually phase differences. Yeah.
So in the normal momentum space, even the 1D systems or 2D systems can have non-trivial topology and churn number. Why here we need at least 4 superconductors to get this non-trivial?
So if you look at to have the non-trivial, you have the churn number. At least you need the 2 momentum, right? At least the K1 and K2, which is actually here is the phi 1 and phi 2. And the third one actually is the tuning parameter. So you can actually tune it with this. It can give you non-trivial and trivial thing. And the fourth one we needed because actually we know the phase is actually not any physical things. Okay, so we need the phase differences. So at least we need one phase which has to be the actually reference point. So that's why we need at least 4 superconductors.
Thank you.
Okay. Yes.
Imagine replacing the quantum dot by an odd electron system in a Coulomb dot field.
Mm-hmm.
And it becomes like a spin problem when the OR is at bound states.
Sorry, I could not understand. Just
so
yeah.
If you replace a quantum dot
Mm-hmm.
by an odd electron system with a Coulomb dot field,
Okay.
then there will be physics of Kondo property.
Yeah.
Then there is a famous OR is a bound state,
Mm-hmm.
iron a bound state, which is like Andre bound state. So if it's worth trying that, it's an additional parameter. Maybe we can chat.
Okay. We can actually we can discuss about it. Thank you.
Any more? Maybe I have a small queries.
Yes.
So normally when we talk about churn number, let's say in 2D systems, K1, K2, the very phase is defined in terms of adiabatic evolutions.
Mm-hmm.
Like we think about electrons adiabatically moving through K space. Now you have a physical phi 1 and phi 2 and you want to control externally, and how do you realize this adiabatic evolution of phi 1? It has to be extremely slow. Let's say, I don't know how this adiabatic condition is satisfied or comparison to do you have?
I think I believe experimentalists can actually control this parameter using some magnetic field. I believe between the resistors. Yeah. Is it?
Adiabatic condition that this very phase appears due to the
Yeah, very slow evolution,
very
right?
slow evolution, so that there is no.
I think we should ask with the experimentalists maybe how can they control adiabatically at least. Yeah.
So if there is no questions, let's thank the speaker. And